And now we have our session of IBM ecosystem. We invite here Dr. Ahmed Katacha. We'll have two speakers. I'm going to introduce the first one, and my colleague Dr. Asma is going to introduce the second one. Okay, so we have our nice session, IBM Quantum Ecosystem, and we have our nice guests and speakers, Dr. Ahmed Al-Katacha and Engine Ahmed Salim. So Dr. Ahmed Al-Katacha leads the quantum business, including quantum strategy formulation and development, as well as quantum computing and research collaboration for IBM Quantum in the Middle East and Africa. Dr. Katacha is an IBM Senior Quantum Ambassador and a Qiskit advocate, as well as a leading researcher in material science, nanotechnology, and quantum computing. His research focuses on practical applications in aerospace, automotive, defense, healthcare, and sustainability.
Also, it's my pleasure to introduce Ahmed Salim, a distinguished technology leader. As a technical leader at IBM, he bridges the gap between business strategy and cutting-edge technology, delivering solutions that create significant competitive advantage. Also, as an IBM ambassador, he is a key educator for quantum computing, and he helped us a lot in monthly series. Okay, thank you.
Okay. Ahmed, you will start.
Yeah. Thank you very much for hosting me. I'm Ahmed Salim, by the way, the second one, okay? We are both Ahmeds. Okay, so first I need to set the floor why we are here as an IBM. We need to have a common understanding about quantum computing, what IBM is doing in this field, where we are starting, and where we are heading in the future. We just need to clear some ambiguity about IBM progress in quantum computing, and we cannot see the future until we see what has been done before, and if there is a promising opportunities in the future that we can make the world more quantum useful and quantum safe. So these are the two missions that IBM declared in all the events. So as an IBM Quantum, it started in IBM research team, and we have more than 3,000 researchers working on different levels of quantum science. And inshallah, Ahmed, my colleague, will go through the roadmap and where exactly IBM and all these researchers are working on. Internally, we have like 6 Nobel holders. We have a lot of 6 national medals of science. Maybe the best team and scientists, they are working for IBM to develop the best quantum computer in the world. So this is a very important a slide, because it's giving you a differentiation between why we need quantum computer. So we definitely in our real life, we have some problems that already we are able to address it using the classical computers, or the computer that we are using on day-to-day, and some problems that we not be able to resolve because of the limitation of the computation capacity that we have as we speak. However, we have this overlap between these two areas. So, driving this from this graph, I want to highlight 2 main terms that we are using in the industry. And why we are keep defining these terms, because still the computer world, it's a new world for all of us. It's not comparable to the architecture, for example. In the ancient Egyptian, they started these temples, building all these buildings, but this is a ready-made science. It's an old science. We know all the basics. We have all the understanding of all its terms. However, in the computer, not only the quantum, we need to align and agree on some terms. So many terms that you are hearing is quantum utility, quantum advantage. What is the quantum utility and the quantum advantage? It might be address one of the questions that has been asked. Quantum utility, which means that some problems I can resolve it by the classical computer and the quantum computer. Okay, so, and this is the era that we are living in right now. This is the quantum utility. quantum advantage, which means some problems we are not able to solve it using the classical computers or the computers that we know. It's only applicable or can be represented by a quantum machine. Okay, so this is in the high level what is the difference between these two, because you might hear it a lot. Okay, IBM is working on 3 main categories: simulation nature, mathematics, and the search optimization. And as you can see, all these industries, IBM has partnership with giant companies in the world. They are doing a huge investment into quantum machine to define the proper use cases and solve a real use case on the problems that they are saving. Examples of these use cases, we have partnership with Vodafone for telecommunication in UK, HSBC in banking, ExxonMobil in the logistics supply chain, CERN, Mercedes, Boeing, and all these different industries, different use cases. We have a set of researchers working hand in hand with all these customers to identify the proper use case and then work on a POC and address and evolve across the board to get a resolution for these problems that are unaddressable by the classical machines. Okay, I'll keep it. So away from this quick introduction about IBM and the history, we need to look what will be ahead. In 2029, large-scale fault-tolerant systems. I think many of you, not all of you, heard about IBM announcement that the next year will be like the fault tolerance, the quantum advantage year, and by 2033 we will reach the fault tolerance. But what does it mean? We need to understand what are these terms and how IBM is progressing its research to reach the quantum fault tolerant. As I mentioned, I'm always like to look into the future, to the past, to be able to judge whether we can progress the technology that we're working on in future or not. So this is a view of the research of Buchabisi. This is one of the main researchers where everything started there. So starting from World War II, it's not a nice memory that they are doing munitions manufacturing. Then they converted to building the first, or put the architecture of the first computer by 1964. And I think the era that we are living now, it's back to building or putting the architecture and the basics of the first computer. After that, after maybe 44 years, IBM was able to build the Frontier. It's a supercomputer that can do around 1 quadrillion. It's 10 to the power 15 flops. Okay, so that was massive. And we are progressing to the research and building now the quantum computers. This is the evolution of building the computer and to spread the knowledge about how to build and the problems that we faced. If you compare between the classical computers, the problem that we faced back then, I think it's easier than the quantum machines and resolving the problems that we are facing currently. Because as you all know, the classical computer based on transistors, maybe it was easier to resolve than the quantum, because the quantum is a faulty, a noisy system, and it has many science and scientific problems that we are working on to resolve as we speak. This is a very important slide, because what do you mean by large scale and how we can achieve the fault tolerance? So large scale, which means IBM is aiming to have or run multiple qubits, maybe hundreds, millions. This is the roadmap, and run it in a way, in a very deep number of gates. It's maybe 100 millions of gates. So this is when it comes into the larger scale. But how we can reach this large scale? Before going to that, as we agree and as we know that the quantum computer, it's a noisy system, which means all the qubits come up with some errors. So it has problems that we need to resolve. So we want first to have an error correction, error detection, to be able to fix or do the error correction, right? So the error detection, that's what we are working on right now. and it has many methodologies or many algorithms to be able to detect the faulty results, and it will be able to fix these errors. How we are doing that? Some people, okay, what they are doing, they are maybe at 2 or 3 qubits, extra qubits, and do a parity check across all these qubits to detect the error. But imagine if you want to deploy this on a large scale, like hundreds, thousands, maybe millions of qubits, imagine this will go exponentially hard to be managed. So this is IBM, this is what we are working on right now, and we have the error correction. The error correction, it has many algorithms that IBM is working on. One of them, what we discovered or released is the dynamic circuit, where we can work hand in hand the quantum computer and HPC. Maybe this will be relevant to Dr. Ahmed Shawki's session. What is the role of HPC working with the quantum machines? So IBM, 3 years back, they started doing or putting or achieving the dynamic circuit. And the dynamic circuit, simply, we need to have part of the circuit running in the quantum machine and interrupt the circuit, read it in a classical information, and the results of the classical information, this will be, it will decide which circuit and how the circuit will be executed in the quantum once again. So we have something like a loop where we can interrupt and reiterate our circuit more and more, okay? So having all these problems and identifying what is the error correction, what is the error mitigation, we need to reach the fault tolerance. The fault tolerance, we have more than 100 million operations without resistance of failure, okay? So we need to get more accurate results out of our quantum system. Just to give all of you about the power of quantum comparing to the existing classical computer. For example, if you want to represent a state of, let's start with maybe 10 qubits, for example. You might need 17 GP, laptop of 17 GP RAM, so you can do this simulation. That's fine. However, if you want to increase this, if you want to represent a state of 30 qubits, which means you need around 2 modern laptops to be able to represent it. However, if you increase the number of qubits and you have like 48 qubits to be simulated, you need supercomputer to do that. It's like, this is the Summit, one of the IBM supercomputer, to be able to represent the 48 qubit state. And by this, if you want to have like 60 qubit, you're going beyond all the classical computer that we have in the universe. And the Blue Jay, this is the, Starling. Starling, this is what IBM targeting to build as part of their roadmap to go beyond this, and they will be able in this, by having this to address some use cases, some applications that never exist before. So if we look into this graph, we can identify, if you remember what I said, this is the pre-utility regime, okay? So we have more problems that can be solved by classical and quantum. However, if you can see this chart, this is the circuit size, and this is the number of qubits. And these are the use cases that has been identified and the strength or the capabilities of the quantum computers that we have as we speak. So if you can see the problems that we can address here, and maybe in the short term, it's relevant to spin modules. However, in the chemistry and the materials, you will find it here in the Blue Jay. So this is promising to be a resolution or problems that could be addressed by Blue Jay as an IBM quantum machine. And this actually chart, if it will evolve, definitely it will shift all these problems to the left, because we will address and identify more problems that will be addressed with more powerful quantum computers. So to drive the fault tolerance, we have these 3 main pillars: scaling beyond the surface code, where we want to address the error correction and the errors to have a clean results. The second thing, a modular architecture fault tolerance, and Ahmed, inshallah, he will show you what we have when it comes into the quantum processor and which processors supporting the modularity. And the third pillar, engineering for fault tolerance. So we will be able to address the error correction with the error mitigation and all these algorithms and techniques to be able to have or to achieve the fault tolerance quantum. By this, I think I will hand over to Ahmed for going through the roadmap. Thank you.
Thank you, Ahmed, so much. So actually, I will start my session by asking a question. What do we need in order to achieve or to start doing quantum computing? So as you can see, what we need is two things. We need a good hardware, and we need also a reliable software. So starting with software, you need something that can help you to encode data, to run the data in a more reliable environment, and can fulfill the requirements of a scientist. It happened to be an ex-colleague in IBM who is DiFicenzo criteria. So you need to have a system in which you can encode data, you manipulate the data through gates, and you can optimize the mapping with the physical qubit, do the measurement, and get the results. And this is what we have been doing since 2016. So we have made a commitment to our user to introduce multiple innovations every year, covering the innovation roadmap, software, and hardware. So I'll touch base quickly with what we have done during years. So we had the pleasure to introduce Qiskit, the Quantum Information Science Kit. It's the most performant SDK worldwide. And every year we have made a commitment to make things happen with the new innovation. So example of that in 2023, in 2024, we introduced the code assistants, which is similar to a ChatGPT. So any user nowadays doesn't need to, in theory, to know programming, but he or she needs to understand the quantum physics or the quantum mechanics in order to model the challenge that you have, write it in, for example, in a few sentences or a paragraph, and plug it into our code assistant, and the code assistant will develop the code for you, and it will help fix it if it did not work. Also, one of the innovation is the optimization. So in order to do quantum computing, you need to go through 4 phases. So you need to start with the data encoding and then move to optimization. Why optimization is important? Because as my colleague said, that we still live in the NESC era. So whatever we start in logical qubit, whatever we do in data encode, we need still to map them in the actual hardware in order to reduce what we refer to as an error. These errors are inevitable for now because we need to correct them or mitigate the errors. And in 2029, we have made a promise that we will enter the fault-tolerant era. So optimization is very important to reduce errors and to increase the depth of the circuits or make more computation using more gates, and this is very important. So we introduce the optimization, the transpiling function, and this year in 2025, it's the year of functions. So we have developed our own ecosystem in which we work directly with startups, and these startups, by design, they innovate. They are good in some areas that they show great results. For example, we have a collaborator called Kipu. Kipu, they are good in optimization. We have logarithmic and multiverse. So each one of them is specialized in quantum machine learning, in optimization and other functions, and we have made their contribution as functions that you can, as a user, call these functions within the other libraries and enjoy the use of these functions in order to fulfill your requirements. And also you are more than welcome to develop your own functions, because Qiskit, as you know, is an open source, and it's an area or a platform or a forum for everyone to innovate. Moving with the hardware. So the first part is the software, then we are moving with the hardware. So every year, similar to what we have done before, we have introduced innovation. So we started back with 3 qubits, then we scale up to 5. And nowadays with Heron R3, we reach 156 qubit. So we jump to we pass through the threshold of 100 qubit. And why 100 qubit is an important threshold? So in practice, if you do quantum circuits with less than 100, this means that you are able to simulate this circuit. So there is no commercial or scientific value of doing quantum computing on systems that is less than 100, because it can be simulated by classical computers. And when we pass or surpass the 100 threshold, there is no way that an existing classical computer can do this type of calculation. So this is a privilege for introducing Heron with 156. So in the next slides, I will divide the presentation into 2 parts. The first part is talking about our the innovation roadmap, covering the quantum processing units, QPUs, that we have developed through the year 24 and 25 and 23. And then I move to cover the QPUs, the chips that we have developed this year and we will be working on the next year in order to achieve the fault tolerant. And I will explain our point of view about how we're going to achieve the fault tolerant, because we believe that we are elevating the discussion from theoretical, experimental approach into more engineering way by providing more insights about what we are going to do. So, starting with Condor. So Condor was the first chip that we have made and exceed the 1,000 qubit. So as you can know that in order to do computation, you need more qubits and you need more gates and you need an accurate system with reliability in order to get the expected results. So one of the chips that we have introduced was Condor, and Condor is 1,121 qubits on one single chip. And in the same year, we introduced Heron. And as you can see, all our QPUs are named after birds. So Heron R1 and R2 and R3. So we started with 133. After Eagle, Eagle was 127 qubit. Then we moved to Heron R1, 133, and then Heron R3, 156. So the technology that we use with Heron R3 is we have 156 with heavy hex. So all the physical qubits are organized in a heavy hex. Heavy hex means that each qubit, which represented as a dot, can be connected with the neighboring 2 qubits or maximum 3, as you can see in the end or in the peripherals. So this technique helped us in order to reduce errors, as you can see significantly when we make a comparison between Eagle. Eagle was 127 and Heron is 156. So we increase number of qubits, we reduce the errors. And also there is another aspect or dimension of the performance of the hardware, which is crosstalk. Crosstalk is a side effect of manufacturing quantum processing units, because once you, for example, connect or initiate physical qubit, there is a tendency for the neighboring qubit to be entangled, which sometimes you don't want to have this behavior. So this is what we refer to crosstalk. So we need to ensure that if we entangle or put a qubit, a physical qubit in superposition or entangle, that this qubit doesn't talk to any other qubit except the one that we have entangled. So crosstalk is very important. And as you can see here in Heron, it's almost 0, which is a good indicator for high performance. Gate time is another performance measure, and it's very important because we need to strike a balance between making the gate time longer in order to achieve or preserve the quantum status or state, and at the same time make it shorter in order to make more computation. So with 90 to 100 nanosecond, this is the optimal that we have reached, because with this number, you can do more, but you cannot lose the quantum status. So as you can see here on R3, all the data, the performance of all our QPUs are available to public. So anyone who has got an IBM ID and has access to our systems, which is available in the cloud, he can log in and go to the public domain and start to get the performance measures of these QPUs. So we don't hide them, we make it public. And we always publish and make a benchmark between what we have done and what others are doing. Flamingo is the next on the scale for Heron. So our technology is modular, which means that we have an analogous of the GPU. So like GPUs, which use stack, we have developed our technology such that you can entangle two QPUs together using our technology, the L-couplers, which ensure that the quantum state is connected and it's not collapsed between two QPUs, which allow us to do more computation, as I have explained previously. And also, this is the physical presentation of the QPU. And with the crossbell, we have multiple connected QPUs, Herons. And this will, for example, provide us with the capability to have multiple Herons in one quantum hardware. So in this example, we have 3 times 160 qubit. So I have explained what we have achieved to date till 2024. Moving toward achieving the fault-tolerant, we have introduced a new set of quantum processing units. So these quantum processing units have been developed in order to meet the requirement of the error correction special code, which we have developed, and we refer to it as a gross code. Why the gross code is important? We've been working with the surface code, which allow us to entangle two physical qubits on a 2D level. But this approach has showed that we need to produce more physical qubits, as my colleague has stated. So in order to compensate the error detection, error correction, and error mitigation, we need to produce more qubits, and this more qubits consumes energy, create more errors and require a lot of correction. And the source code, as per our researchers, is not helping. So this is why we have changed our strategy, and we moved with the gross code. So the gross code, it's a mathematical approach that allow us to do error correction in a surface, which I refer to it as a 3D topology, which looks like a donut. So in this donut, a theoretical donut, or the 3D topology, we connect qubits using C-couplers, increasing the possibility for connecting each physical qubit with 6 other qubits. So in the heavy hex, as I mentioned, because it's 2D, using surface code, maximum we can connect 2 or 3, but here we can connect 6. And this breakthrough allow us to do or achieve error correction very quickly, but it has made an engineering challenge for us to manufacture new types of QPUs. And this approach has been welcomed by leaders in research like IDC. They said that we have introduced a game changer and changing the whole conversation from research experimental-based approaches into an engineering approach, which can ensure the scientific and non-scientific community that we are heading toward achieve the fault tolerant. So I will start with the gross code. So the gross code simply, it's a mathematical approach in which we ensure that we increase the connectivity of the physical qubits by just imaginarily turn the space to make it like a donut. So with this theoretical approach, we have shown that we were able to reduce number of qubits, physical qubits, by more than 10. And the beauty of this approach that it comes in dozens. So it comes in multiple. It allows us to manufacture our physical QPUs, physical qubits in 12 multiple, which is something amazing. And we have published this, and it has made a lot of noise in the scientific community, and it has been published in the cover of Nature. So basically what we are trying to do, so in 2025, we managed to manufacture the first chip, the first QPU, which fulfill the requirement for the gross code. And we have proved that the gross code is really the solution for the fault tolerant, and we introduced Loon. Loon is a chip that can produce 2 logical qubits corrected and without the need for error mitigation. And the technology that we have used is the C-couplers. And we have demonstrated the effectiveness of the C-couplers to make this happen. Also, we have introduced another chip, Nighthawk, in the same year. And Nighthawk is another demonstration of the power of this type of manufacturing in order to achieve the fault tolerant, but with more qubits. In 2026, we will introduce Kookaburra. Kookaburra is a demonstration of a chip in which we increase or hit the 100 qubit and extend the use of the C-couplers in order to bring to the world the first logical processing unit for quantum that can work like a quantum memory. In 2027, we will introduce Kokatu, introducing another types of couplers, which is the L couplers, in which we can entangle or ensure that the quantum states between 2 quantum processing units are preserved. And in 2028, 2029, we will introduce Starling. In Starling, we will extend the use of the L couplers, and we will introduce the Magic State Factory, such that we will be able to offer our users a new type of gates, which is the T gates. So, because nowadays, all what we can do is use the C node for TOEFL gates, but with the Magic State, we can do also the T-types gates. So this is just a demonstration about the ideas which I have explained. So in Heron, as you can see, it's a two-dimension connection. So each qubit can be connected to 2 or maximum 3. But with Loon, we have attunable couplers, C couplers, which can show the architecture of the 6-way connectivity. So this is another demonstration in which we have proven to have 6-way connectivity, which reduce the possibility to use more qubits, offer our users more computation, and less effort to do the cross code, which will assure that we reach the fault tolerant. All right, now, as you can see, there is another type of qubits or QPUs, which is the Nighthawk. So the Nighthawk is the same structure of the Loon, but with more qubits, and it's based on what we refer to square. So in order to explain the advantage for the square-based connectivity and the heavy hex connectivity, next year we will hit the quantum advantage in material science. And this is very important to prepare for this event by introducing the right QPU that will achieve this. And in order to do a demonstration, we have made a comparison between how Heron R3, which is the best heavy hex structure in IBM, will behave in comparison with Nighthawk. One example is, for example, for ethane. If we wanted to simulate ethane, so in this type of calculation, we need for the square, which is the new architecture, 27 qubits. Whereas in Heron R3, we need 65. This is an extra number of qubits that will make it difficult for us to optimize the circuit. So the square architecture based on the tunable coupler technology has provided us with less number of qubits, less errors, and high accuracy. And if we, for example, compare this with benzene, carbon, a dimer of carbon, and the 4Fe4S, you see that there is a trend that we reduce number of qubits, we increase, and also we reduce number of gates, which means that we can do more computation. This is an actual or a topological presentation of what is the difference between Nighthawk and Heron. So the difference is, as you can see here in the bottom, that each physical qubit can connect only to 2, which will limit the way how we deal with errors. So we need to encode more qubits in order to overcome the noisy errors which will happen. But here, in the square architecture, in between, we have the couplers which allow us to connect more qubits. So 1 qubit can be connected with 6. This is another example, and as you can see, we have published this, so we don't hide anything from the scientific community, and we share it with the scientific community, and we are pleased to present this structure. Okay, Now I will change the topic, talking about if we are users and we wanted to pick what modality. So in market, there are different modality that we can use quantum computing. So some of those modalities are based on superconducting qubits, which we call transmon. Some of them, they are based on cold atom, like the ones which Professor Murad was working on. Some modalities are photonics, some other modalities are based on trapped ions. So in order to provide a guidance, what we believe is, in order to do an assessment of the hardware, you need to look into different aspects, because no one will buy a car because, for example, it's fast. No one will buy a car because it has 4 wheels. So you need to look into differentiators. And in our views, because we are the leader in this field, we always put the measure and the other service providers, they follow. So we believe that speed is very important, because you don't expect that you put, for example, your program in a computer, on a hardware, and you wait for results. So there should be a reasonable time for processing. So speed is very important. I'm not talking about the time, the waiting time. I'm talking about the processing time. And also scale. This means that the technology that you are using is scalable. So you don't want to end up with a technology that cannot be scaled in order to achieve, for example, certain numbers of qubit that fulfill your requirements. So this is very important. And also performance. And there are multiple measures for performance. So some of them about the coherence time, T1, T2, and the fidelity of the 2-qubit gate and 1-qubit gate. And we always publish this and make it available or in public use. And also one important thing, because most of us, they don't have the luxury to buy a quantum computer, because this is not something that you do every day. So it's very important for you to ensure that the system that you are using is reliable and the system has latency that can fulfill you. And what I have discovered, that some of the modality is available on other clouds or other platforms. This creates another problem about data security. So dealing with one service provider is much, much better than dealing with multiple. So these are, and of course, the hidden one is the cost. Cost is very important. If you can compare what you can do in $1 with equivalent to what you can do with others. So to cut the story short, we have mapped what is available in market in terms of number of qubits and the error. And as you can see, there is the boundary of the 100 qubit. And I need to emphasize that 100 qubit is important, because whatever you can do in less than 100 can be simulated. So you are wasting your time and effort if you invest or do any calculation in a device or a modality which is less than 100. And there is another advice, because, and Dr. Ahmed, he knows about it. So what we are targeting to achieve is a fault-tolerant universal machine that fulfill the deficiency criteria. So be aware of this. So as you can see, in market, there is only IBM and Google who had the 100 qubit, and we achieved 156, and we are expected to hit the 200 qubit soon. I'm not going to talk about other modalities, but as you can see, either they are good in error, but they don't have a scalability, they don't have qubit, and some of them, they are good with a qubit, but with less fidelity. Another aspect is talking about the speed, which is a measure of the SDK. So Qiskit is the most performing SDK. It's an open source. And this has been assessed in the eye of the users. And I bet that most of you, if not all, have been working with Qiskit, and you know it maybe better than me. So making a comparison between number of projects. So worldwide, Qiskit has been used in more projects than others. And also what you can do in Qiskit in 5 minutes requires 27 hours with other modality. So be aware of this. And this has been published, this paper, this benchmark paper, we refer to it with the word bench press, has been published and made public. So the idea of this, we compared our SDK with many others SDKs, and we make a comparison about how efficient is Qiskit in comparison with others, using, making an apple-to-apple comparison. So we have picked certain databases in which we apply the calculation with, and this is the results. So in conclusion of that paper, Qiskit is faster with high quality and extensibility. And when users have been asked about Qiskit, so they mentioned that it's the most the performant source and the most reliable one. I think I need to pause here. I left this link for my LinkedIn detail, and I'm happy with to have your questions if there is any question, and apologies if it was too long. QBUs, we sell them like souvenirs. No, I'm just kidding. No. No, actually, we have some of them. We use them for other research and development. Some of them, they are kept in our research centers across the world. So if it happens, and it will be our honor, if you come to Yorktown, for example, you will find some samples of them. Some other of them, we use them to do some benchmark, for example. So one of the questions, if I wanted to do a simulation of 27 qubit or 127 qubit, this is example here in the comparison that we did between eagle, for example, and heron. So eagle is retiring, so it's no more available, but we still have some machines in which we run to do a benchmark with heron, for example. So part of them, we reuse them for research and development and calibration. Yes?
It's mentioned that heron achieved 0 crosstalk.
Yes.
Going from heron to loon, I saw there the slide showing the structure. You mentioned heron has only 2 connections. Yes, this is the previous slide.
Yes.
No, the one with
This one?
no. Yes, this one.
This one, okay.
Yeah. Okay, going from heron to loon. First, wouldn't that increase the crosstalk or make it like there's more coupling there because there's more compact qubits?
Okay. Let me explain. So in engineering the dimension, so we are not doing science. So scientists, for example, will tell us that this architecture, this is the phases of research. Science will tell us that this is the best architecture. Now it's the role of engineers to tune it. So in order to tune it, we have multiple objectives to achieve. So talking about crosstalk. Crosstalk as a problem is a function of many parameters. But let's say that one of these parameters that we want to optimize is the distance between 2 physical qubits. So we can solve this problem by trying to make them, for example, while manufacturing close or far away, and we optimize it. So if it's only one factor, but I can guarantee you that there are at least 20. So it's not an easy engineering problem. So once this problem is done, the architecture, because it's a heavy hex architecture, is there. It has created another problem. This problem is, I need more qubits in order to present one logical qubit. So in order to simplify this problem, when you initiate your circuit, so in your, for example, Jupyter notebook, you refer to the qubit with Q0, Q1. So this is a logical qubit. But the black box, when you send your job, it's our role to optimize it, to map it. So when we map it, for example, you start with 10 qubit. Maybe when we map it, we need 100, maybe, or less. And you can see that there is some other functions in Qiskit which will optimize number of circuits, and it will show you how your circuit is mapped. And you can physically see in Qiskit how the mapping happened. So this mapping with this structure require more qubits. So in order to solve this problem, we have come up with the square structure, which allow us to do 6 connections. And that was the solution of another problem. So crosstalk has nothing to do directly with the 6 or square structure. Any question? So we were thinking about, yes.
I have a question.
Yes, please.
In one of the slides, you compare different technologies.
Yes. Yeah, the modalities.
Yeah. What you did not discuss, but I think is very interesting, is the cost of running.
Yeah, I did, actually. No. Actually, I did not explain it, but it's in the slide. And I will explain if you want.
Thank you. My name is Jan Blommer, by the way. Because during research, if you have a single project, you can say, okay, I'm not so interested in the run cost. But at some stage in the coming years, when we are doing something like production, whether it's scientific production or business production, the run cost will become important.
Excellent.
Yeah.
Yeah, I agree with you 100%. And this is why I said that speed, scale, performance, reliability, and cost is directed, is associated with all of them. And I will explain why. Because, so suppose that you wanted to run a circuit. And this is what we have done here in the bridge. We have a paper, I can share it with you. It's called the bench press. So the idea of the bench press paper is, if I had a certain database or a repository of some problems, and I wanted to run the same problem with different SDKs, for example, with X, Y, Z, how long it will take, how accurate is the answer, because the answer is there in the database, and also how many qubits I will need to initiate. So all these questions have been answered in that paper, and based on that, we have made this, for example, summary. So here, as you can see, we have different comparisons. So we have Circ, we have Ticket of Quantinuum, Penny Lane, and Qiskit. And we have more. Also, we make a comparison with simulators, QCODA. So in terms of time, what you can do with IBM in 5 minutes require 27 hours. Going to the way how they structure their prices, we discover that we are cheaper in comparison with these people by 1,200 times, and in some cases, 70,000 times. So cost is there. Maybe we've been perceived as per 1 minute that we are expensive, But what you can do in 1 minute in comparison with others is really valuable, and it has already been proven scientifically with the bench press paper, which I can share with you. So yes, I agree with you, cost is important. The other dimension is time. So because of the superconductivity, the technology is very fast and the gate time is small. And this is how we can, in our engineers, they strike a balance between keeping the quantum state uncollapsed for a while and make it fast. Because some technologies, for example, like the trapped ions or cold atoms, they have longer coherence time. And in order to decohere, you need additional time. So to manipulate qubits, which are entangled, it required additional time. And another challenge is that this technology, for now, is not scalable. They did not reach 100 qubit or more for now. So these challenges make it more expensive as an offer for the users. But thank you very much for highlighting this, because it's there, but I did not discuss it in a proper way.
Let's say, I'm interested in the business running cost. That's
You're right.
But that's also a wider concept, not just the cost per minute, I would say.
Yeah, I agree with you.
Yeah. Then there's another issue, and I'm working with Dr. Taha on modeling molecules, smaller molecules, or even electronic transitions in atoms and in ions. That's the concept of more accurate results before achieving a speed up. Yeah. What is your comment on that?
Actually, I was about to discuss this because my background is in material science, and we've been collaborating with Riken University in Japan. So we had a strategic partnership with Riken University in which we use a new concept which called the quantum-centric supercomputing. So in this work, which has been published in Nature, we demonstrated how we can hand by hand use HPC, classical calculations, along with quantum in order to achieve results better than, for example, CSCD and DFT for molecular computational modeling and simulation, using an algorithm which we refer to like sample-based quantum diagonalization. So it's a combination. So the HPC has been used in order to diagonalize and get the parameter of the circuit, and then feeding up into a smaller problems in order to achieve the more accurate results. So also this is an example of using quantum classical or quantum for material science. But if you are worried about the cost, how we think with our customers. So it depends on how you want to use quantum computing. So some people, they wanted to use quantum computing for education. So for education, you don't need to buy access. All that you need is just to sign in, get into IBM ID, and have the 10-minute free access, which is more than enough. If you want, for example, to try more things, then we believe that pay as you go is the best because it's relatively good. If you want to do research, we have two offers. One of them is the Flexi, which like the phone, the prepaid. So you buy the access and you have 1 year to finish it. So it's handy. And if you want to do hardcore research, then you need to buy a premium access, and we can help you to calculate what sort of capacity you need. And we use a unit called the Quantum Allocation Unit, QAU. So this will depend on the size of the data, how big is your data, what you are doing, the shots that you need to run in order to achieve an accurate result. So all these dimensions are taken into consideration to help you to pick the right plan. So we are like Vodafone, so we help you.
Hello, thank you so much, Ahmed, for the great presentation, although I missed a little bit of it. I just want to ask more about the error correction. So what is the state of the art? I've been like reading the latest paper, I think it was in 2024, but I'm excited to know like what's the state of the art in terms of error correction in 2025 and IBM's like current hardware.
So as I said, error correction is related to two parts. So the first part is to pick the right approach, which is similar to the approach that we did 80 years ago. So just to provide an explanation of the severity of error correction. So why do we need error correction? So we need error correction because the nanotechnology that we are using still have a quantum phenomena that create a lot of noise. And this type of noise has been detected back in 1940. And the first type of problem was the flip bit problem. So for example, if we have transistors, we moved from vacuum tube to transistors, and in order to set the voltage, for example, for 0 by 0.5, let's say, not all transistors will act similarly for 0.5. Some of them will have 0.5, 0.4, 0.6, and that problem was 80 years ago, and we have corrected this problem with the flip bit codes. Now, in the quantum era, the problem is more complicated because we need to fix the amplitude and the phase. And we've been experimenting with the surface code because our hardware is 2D. So in 2D, you need to encode more qubits in order to act for error detection and error mitigation or correction. And this is not handy. Why? Because, for example, if we wanted to break, I think Dr. Hisham will like this, if we wanted to break the RSA, the 2048 RSA, currently we need 20 million physical qubits, which is not available for two reasons. From manufacturing and from error correction, because it's really crazy to error correct 20 million qubits. This is why surface code is going nowhere. This is our view. We invested in another approach, which is called the gross code. In the gross code, the challenge is with the topology. So we need to have a donut topology in order to increase connectivity. So this represents an engineering challenge for us, but we have made it with Loon. So in order to implement the gross code with the donut topology, the 3D topology, we have come up with a new design. We demonstrated this with a chip called Loon. And in Loon, we introduced a new technology called the C-couplers. C-couplers allowed us to connect 6 qubits. So it's more connectivity, which ensure that we have less errors and more accurate results. So this is in brief what we have done for this year, and next year we will have Kookaburra, Kokato, and Starling in 2029.
And with this technique, have you reached below threshold in error correction, or is still a little bit far?
We increase number of gates. So how we can translate this? Reducing errors means that you have more gates to do calculation because there is 2 dimensions. So you need to increase number of qubits to a certain limit because you encode data exponentially. So as I have seen, or my colleague has shown you, so data goes exponentially. So with 200, we have the capability to encode 2 to the power 200 bits, which is really massive. So we need to stop, for example, at certain number of qubit, but what is more important is the depth, gates. What we wanted to do is to reach 100 million gates. And in order to reach 100 million gates, we need to invest in the gross code. And we have demonstrated this here in Nighthawk. So we made a comparison between Nighthawk and Heron. As you can see, we reduce number of physical qubits needed to encode the data. So for example, to simulate ethane or benzene with the using the square, we have reduced the number of qubit with 55 and the C note number with 380. So we reduce qubit and we reduce number of gates, which allow us to do more computation.
Yeah, thank you so much.
My pleasure.
Thank you, Dr. Ahmed, for your valuable.
Thank you very much, and please forgive me for this long time.
Okay, now let's have a short break, about 5 minutes only, and let's go back. Thank you.